Up to now, we've been doing numeric calculations, which are required in many real-world applications. Take the simple example of finding the solutions to a quadratic equation. We can quickly find the solutions numerically when we have the coefficients. However, sometimes we get imaginary roots. How can we determine when the solutions are real? If we look at the symbolic solution, we see that the expression inside the square root must be positive to have real roots. Let's see how we get to this solution using MATLAB and the Symbolic Math Toolbox. The first step is to define symbolic variables using the symbs command. Symbolic variables differ from the numeric variables we've used so far because we don't have to assign value to them. We simply declare their existence and we can use them in calculations. Like here, we enter the generic quadratic equation and assign the expression to the variable y. Notice that y automatically becomes a symbolic variable even though we didn't declare it as one. Now, to find the symbolic solution, we use the solve function while setting y equal to 0 and specifying x as the variable to solve for. And bingo! The solve function returns a variable with the two solutions that match the quadratic formula. But wait a second, there's something different about this last command. Because a single equal sign is the assignment operator, we used two equal signs to create a symbolic equation. Now, what if we need to apply our solution to a specific example? In other words, we have to replace the symbolic variables a, b, and c with fixed values. No problem. The subs function replaces symbolic variables with numbers or other symbolic expressions. Here's how it works. We need three inputs: the expression we wish to evaluate, the symbolic variables to replace, and the values to substitute in for the symbolic variables. The result is kept as an exact symbolic solution rather than a numeric approximation. Perhaps you've noticed our solution is not fully simplified. Let's fix that using the simplify function. There we go, an exact solution to our quadratic equation. In many cases, we still need a numeric representation of our symbolic results. Again, no problem. We use the Variable Precision Arithmetic, or VPA function, to view the exact solution as a number. The second input to the VPA function specifies the number of digits to include in the output, and the output is still a symbolic variable. We have now worked through the essentials of solving an equation symbolically, and you can use these techniques to solve a wide variety of problems. Before we close, here are a few examples from other applications that often arise, like finding integrals, doing series expansions, and plotting equations of one or more variables. Now, put away the pen and paper and try solving a few problems in MATLAB yourself.